Okay, so what we're going to do here is we're going to find missing sides and missing angles, and we're going to start with a situation, an outdoor situation. So let's give ourselves some measuring instruments, go outside and see some real buildings, or in this case a monument that we want to try and measure, just to practice here our trigonometric skills, if you like. Alright, so what I'm going to do is bring up a little drawing here of a monument, a vertical monument, and we're going to give ourselves a platform and put ourselves in a bucket at exactly eye level with the top of the monument. Okay, so we can now draw a line, if we had a laser, let's say, from the eye level here across to the top of the monument, which is exactly horizontal, parallel with the level ground here. So let's now draw on our right angle, because if the monument is vertical, hopefully it is, then we've made a right angle now with the monument. Okay, so now let's again take our laser and draw it down from this point here to the base of the monument to complete our right angled triangle. And let's give ourselves a couple of side lengths. We could have, let's say this is 12 meters, and let's put all measurements in meters, and I won't have to keep writing. All measurements in meters, and let's make the hypotenuse here of our triangle 15. If this is the angle that we're interested in, then this is going to be the adjacent side. If we were looking at this angle here, then obviously the height of the monument, would be the adjacent side of the triangle. Okay, but at the moment it's this side here, so we've got an adjacent and a hypotenuse, and we don't know what the height of the monument is. So how are we going to find out the height of the monument if we're given that this is 12, we've measured this horizontal length as 12, and the hypotenuse here, the diagonal going down here, at 15? Well, using Pythagoras. So let's start with Pythagoras and then move on to the trigonometric ratios. So by Pythagoras, we have the hypotenuse, which is 15 squared, equals the sum of the squares on the other two sides. So we have 12 squared plus h squared. So now rearranging this, we'll have h squared, subtract 12 squared from both sides, and we'll have 15 squared minus 12 squared. And therefore h squared equals 15 squared, 225, and 12 squared, 144, equals, if I think about, let's increase that to 150, so that we 231 subtract 150 gives us 81. Remember, always work over to the side if the mental arithmetic is a little bit too risky. So 8 squared is 81, and h works out to be a nice tidy 9, because the square root of 81 is 9. So h equals 9. So we've solved that. We've already found the height of the monument, but before we pack up and go home, what was the angle, I wonder, up here between this horizontal line, this distance line, and the diagonal distance from this point to the base of the monument? Well, we can find that out using trigonometry, using the trigonometric ratios. So, how are we going to do that? Well, if we think of the lengths that we've got here, let's remove h equals 9, pretend we don't know that, and think of the lengths that we have remaining. So we have 12 and 15. So we can say Well, what are these sides? This is the adjacent and this is the hypotenuse. We remember our mnemonic, which is sine equals the opposite over the hypotenuse, cosine equals the adjacent over the hypotenuse, and tan equals the opposite over the adjacent. Okay, we remember that as SOHCAHTOA. So in this case, we've got the adjacent over the hypotenuse as a possible ratio we could use. In other words, we want to use cosine. So if we want to find cosine of, let's call this theta, which is conventional. The Greek letter theta is often used for an angle measurement. So cosine of theta is our adjacent over our hypotenuse, which is 12 over 15. Okay, well, we can immediately simplify that. If we divide top and bottom by 3, we'll have 4 over 12 divided by 3 is 4, and 15 divided by 3 is 5. So it's the cosine of theta equals now 4/5. At this point, it would be lovely if we had something that we could recognize here. Okay, if we had something like root 3 over 2, or a half, or root 2 over 2, or 1 over root 2, or even something like root 6 minus root 2 over 4. If it magically came out like that, then we'd immediately know what kind of triangle we had, and so we'd know what the angle would be. Either it would be a 30, 60, 90 triangle, and we could work out whether this is 30 or 60, or it would be a 45, 45, 90, or it would be a 15, 75. But it's obviously none of those angles, so it's what I call an in-between angle. So it's not a straightforward, one of those magical angles. So what do? How do we solve this? Well, what's it asking? It's asking us what is theta given that we have the ratio. We now have 4 over 5 as the ratio, 4:5 ratio. So what angle, the cosine of what angle, will give us that ratio? Now, to do that, we just need to look at some tables. We look at the cosine tables, or we simply go to our calculator. We find that ratio, 4/5, and then we look back and see what the angle is that produces it, the cosine of that angle. Now, this is all done for us on a calculator, and usually on a calculator, we're given the symbol. It's usually on the same button as the cosine, and it looks like this, cosine, and it looks like to the -1. Now we need to be careful here. This is called the inverse cosine, but in fact it's not to the power of -1, so it's not 1 over cosine, which is actually something that we call 1 over the cosine equals the secant, which we just write sec. So that's a reciprocal function. It's the reciprocal function of the cosine. And in the second part of this video, we'll have a look in more detail at what the secant is exactly and why it's called secant. Okay, but for the moment, important just to note that the inverse of the cosine doesn't mean 1 over cosine, which is the secant. So it's better actually, instead of thinking of it as cosine to the -1, which is not, as something called the arc cosine, like that, arc cosine or arc cos. And the arc cosine is basically asking this question, exactly the question that we were asking here. It's saying, given that we've got any given ratio, in this case 4/5 or 4:5, then what is the angle that produces that? So what we can say is the inverse cosine of 4/5 equals, and we simply have to look this up on our calculator. Okay, so if I find my inverse cosine sine, and type in 4 divided by 5. That will give me a value of 36.8698, and on those numbers go. So we'll just say fine to have it just to 4 decimal places here. And if our inverse cosine of 4/5 equals 36.8698, then as it's an angle, we're going to say is approximately equal to 37 degrees. Now, it is only an approximation. It's a pretty good approximation, but it is only an approximation because we've had to go into decimals. Okay, we haven't been able to work in exact form, and therefore we can't be entirely accurate, but this is very, very close. Okay, so that's dealt with. Let's just erase all those workings and think of a slightly different problem. What if we were given one of our special triangles? So what if, for example, we were able to move our man to this point here, which is a 45-degree angle like this. Okay, so let's move him up and say now we're going to work in one of these special right triangles, which is a 45, 45, 90 triangle. Well, if we're lucky enough to get this situation, then we can simply sketch our basic triangle, basic 45-degree triangle, which we know is a 1, 1, root 2 ratio of the sides. That gives us any value that we want. If we know the angle, let's choose this one here, we could equally have chosen this one here, then we can say the sine of 45 degrees is 1, okay, opposite over hypotenuse, 1 over root 2, or multiplying through by root 2 over root 2 gives us root 2, 2, and it's usually expressed like that. Cosine of 45 degrees is the same, and like that, and the tan of 45 degrees, if we haven't memorized it, is 1 over 1, which is 1, opposite over adjacent. So we can use that information again to work out the height of the monument. Let's say the height is what we want to try and find then. And this time we know, let's say we know the hypotenuse, and let's say we know that it's 10. Okay, in that case, what have we got? We've got the opposite. If I draw an angle, you can see that's definitely opposite the angle. So the arrow, rather, sorry, pointing to the monument. So that tells us that that's definitely the opposite. If you want to know what this is, well, it's always the case that the angle opposite the right angle in the corner here is the hypotenuse. So what have we got? We've got the opposite over the hypotenuse. In other words, we've got sine. Sine 45 degrees equals h over the hypotenuse, which is 10. Sine 45 degrees then is root 2 over 2 equals h over 10. And now we want to rationalize our equation. In other words, we want to multiply both sides by 10 to give us 10 over 2, 10 times root 2 over 2 equals h. So h must equal 5 root 2 meters. Now we can leave it at that because this time we do have an exact value, and although we might be asked to convert it to decimal, which is fine, we won't get anything as exact as 5 root 2. So that is our answer. Okay, now what have we done so far? So far we've been measuring with our man right at the top of the monument here something that's called the angle of, if it's going down, if we're measuring it downwards, the angle of depression. Okay? Now what we're going to do is bring him down to the bottom of the monument. So let's just remove this working out and remove these lines and bring him in here. Okay. We now draw our lines to the horizontal and to the top of the monument. But in fact, there's a slightly different situation when we're working down at the bottom of the monument, in that we can't actually crawl along the floor, and certainly there might be things in the way if we try to measure straight across here. So we're forced to make an eye level line. So let's go like this. And so this distance here is only to the bottom of the column, as it happens. We have to add on then at the end this height here, because we're not going to be taking account of this in our trigonometry. Okay, so we've got h1 now as being this length here. And if we if we shoot our laser up to the top of the monument here, and then we get a measurement for this as, say, I don't know, 21, let's say. And let's say we've positioned our man, and again he's got some way of measuring this so that he's exactly not only 21 meters from the top of the monument, but he deliberately has placed himself very sensibly with a 30-degree angle here. So once again, we can draw our 30, this time our 30, not accurate at all, but it doesn't matter, because all it is a sketch that shows what we've got here. Our short side is 1, our hypotenuse, the longest side, is 2, and we'll remember that this is root 3 in a 30, 60, 90 triangle. So good. From here we can tell our sine, cosine and tan. So now let's find the height of the monument. Well, in this case we've got opposite over hypotenuse. So actually I'm going to change that. Let's make this a little bit more interesting. And instead of doing sine again, let's bring it down to here so that it's more plausible that we know the distance now that we just measure along the ground here to the monument, and we want to find, we don't necessarily want to find the hypotenuse here, the diagonal, but we certainly want to find the height of the monument. Okay, so what have we got? We've got the opposite. Okay, again, if we draw an arrow, we can clearly see that h1 is opposite to the angle. If we want to know what this is, and we're a bit forgetful, well, don't forget that the hypotenuse is very easy to identify. The hypotenuse is opposite the right angle. So if this is the hypotenuse, sometimes spelt with an H, but hypotenuse is perfectly okay. So if this is the hypotenuse, then this must be the other angle. We know this is the opposite, which is the adjacent. Okay, so 21 meters is our adjacent. So if we're dealing with adjacent and opposite, opposite over adjacent is tan. And we know that tan of 30 degrees is 1 over root 3. From our basic triangle here, our 30, 60, 90 triangle. Okay, so in that case, we can immediately move to our calculation. We're going to say that the tan of 30 degrees, which is 1 over root 3, must then equal h1 over the adjacent, which is 21. Now, how do we sort this little equation out? Well, first of all, we want to get h1 on its own, so we're going to multiply both sides by 21. So we now have 21 on the left-hand side times 1, which is 21, divided by root 3, root 3 equals h1. So h1 is 21 divided by root 3. And again, that is an exact answer, so we could leave it at that. But if we didn't want to, if we were given the problem of, well, give it to me in decimal form, then we could convert it simply by saying it's approximately equal to, so remember, approximately equal to 21 divided by, well, what is root 3? Root 3 is between root 1 and root 4, and it's more than root 2, which is about 1.4, so it's about 1.7. We can only say about 1.7. And again, you can easily do this calculation by hand. If, though, you're working in trigonometry, you normally have a calculator to hand. So I'm just going to use my calculator here. 210 divided by 17 is what we've got here, and 210 divided by 17 gives us, there we go, 12 point, it's a recurring decimal, but it's a very long one, so I'm just going to do it to 2 decimal places, 12.35, and I'll say to 2 decimal places, meters. Okay, so these are the sort of problems that you're going to get in the sort of functional skills exam paper or test. Very often, as I say, it's given in the form of an angle and one side. Sometimes it's 2 sides, in which case you would usually use Pythagoras. And the other possibility is that they ask you to find the angle. If you find the angle, then you're going to be using either, so let's write, to find the angle, given a couple of sides, then you're going to be using either arc sine, which is usually, on the calculator at least, called the inverse angle, inverse sine, so the inverse ratio, the inverse of sine, or it's going to be the arc of cosine, which is cos, inverse of cos, or it's going to be arc of tan that you're going to use, which is inverse of tan. So I think that covers all those sorts of questions, but what you obviously want to do now is to go to practice, and there'll be a practice video for you to have a go at. Now, back into a little bit of theory just to finish off this video. We mentioned in the video that there are some other functions which are the reciprocal of, for example, cosine. And the reciprocal of cosine, and I'll explain what reciprocal means in a moment, is the secant. So I'm going to just now explain what the secant is and why. Initially, all I need to do is explain why it's called the secant. Secant actually means the line that cuts. But before we actually see what the secant is and why it's called the secant, let's just remember what we did with the tangent. Tangent was also something that was a little bit mysterious. Why is the third function, the tangent ratio, why is it called tangent? Well, here's a tangent, and we saw that there was a right-angled triangle here, and there seemed to be no relationship between the opposite over the adjacent, which is the tangent, to a line, which we call a tangent, when it doesn't cut the circle but just touches it at, well, in this case, this point here, at right angles to the hypotenuse. Why would it be called the tangent? And to answer that, we simply change the triangle. So we mirrored it, and then we moved it up to the tangent. It's in the same proportion, it's the same ratio of sides and the same angles, but now we can see that the opposite, the sort of top term, the numerator, if you like, of the ratio, is actually sitting on the tangent. And so that's a good way of explaining why we use the term tangent. Now, similarly with the secant, what we're doing is looking for a secant, a line that doesn't touch the circle but actually cuts through it. Well, we've got 2 secants on here. We've got one that goes vertically down through the circle, but the one that we're interested in is the one that follows along this line here. In other words, it gives us, in this case, the hypotenuse sitting on the secant. Now, that explains why we would call the secant. It's because, seen in this way, the secant is defined, and I'll call it sec. It's defined as the hypotenuse. Let's write it out in full. The hypotenuse divided by the adjacent side. Whoops, there we go. So that gives us a fourth function. We don't often use it. It is used in calculus, but you don't really come across it until you until you move into advanced mathematics. But it's there, and it's useful perhaps to know what it is. So if that's the secant, that gives us, well, let's just review what we've got here. The sine is the opposite over the hypotenuse. Okay, so it's the opposite, the green one here over the white one here, the hypotenuse. So that's one sort of permutation, one ratio that we can have in this triangular arrangement. The cosine, secant, so we're on the ka here, is the adjacent over the hypotenuse, and the tangent, well, that's the opposite over the adjacent. So you can see that the secant is the reciprocal. It's the inverse, if you like, but in a different sense to the one that we were using earlier. It's 1 over the cosine. Okay, so the secant, and we use 3 letters usually. So actually, let's just replace this with the 3 letters for our secant functions. So we have sine, cosine, and tan. Now we've got secant, and secant relates very strongly to cosine. Why? Because while cosine is adjacent over hypotenuse, secant is hypotenuse over adjacent. Okay? So what relates to sine? Well, we call the next function, let's say, I don't want to use the word inverse, because that means something else, as we've seen. But the next trigonometric ratio that we want to fill in here is cosecant. And if we abbreviate that, we abbreviate it to CSC, cosecant. And if secant is hypotenuse over adjacent, you won't be surprised to find that cosecant is the hypotenuse over the opposite. Okay, so the hypotenuse, the white here, over the green, the opposite. Finally, we have cotangent then, which is cot, which is the adjacent over the opposite. And you can see then we've listed out all the possible permutations. These ones, the cosecant and the cotangent, let's just put a little star here, are rarely used. But sometimes they're mentioned, so it's good to know what they are. They're simply, rather than the opposite over the adjacent over the opposite, or with the cosecant, the hypotenuse over the opposite. Okay, so they relate. Cosecant relates to sine, and cotangent relates to tangent, as you might expect from the name. But they're rarely used. This one here, let's give it a little exclamation symbol, sometimes used. So the secant is worth knowing because it's often mentioned. It's also very often mentioned in geometry. It's important to know that it is this line that cuts through rather than the tangent which just kisses, if you like, the circle. So that's the secant. But of course the main trigonometric ratios are these ones here. The sine, cosine and tangent, which you remember by so, ka, toa. Okay, so I hope that's helpful. Again,